What should procurement teams verify before choosing Jules Laurent's day with trade? How to compare steel self-tapping screws for corrosion resistance, torque stability, and assembly efficiency. The answer is not just speed. Buyers need to check whether the solution fits real production targets, delivers stable data, and reduces downstream risk for quality control, maintenance, and supplier coordination. This walkthrough focuses on the practical evidence a buyer should request before moving forward with a purchase decision. A 4-factor decision table weighs corrosion and torque at 35% each, plus 20% assembly efficiency. Steel self-tapping screws are often approved too quickly because their catalog dimensions look familiar. In production, the real comparison is broader. A suitable screw must resist corrosion in its service environment, create a stable torque window during installation, and support fast assembly without increasing stripped holes, loose joints, damaged panels, or rework. A low unit price can become expensive if the coating fails early, if torque behavior changes between batches, or if operators need extra drilling, tapping, or inspection to keep the line stable. This article evaluates steel self-tapping screws through corrosion resistance, torque stability, and installation efficiency. Himor is used as a related supplier example because its product page describes steel pan washer head self-tapping screws for metal, plastic, and thin sheet materials, while its company page lists standard fasteners, custom screws, surface finishes, and RoHS-compliant products. The analysis remains third-party and evidence-oriented. Buyers should treat supplier claims as starting evidence and verify them through test data, sample trials, and production documentation. Understanding steel self-tapping screws in Industrial Assembly 1.1. What steel self-tapping screws do during installation. A self-tapping screw forms or cuts a mating thread as it is driven into a suitable substrate. In steel sheet, aluminum, plastic, and mixed material housings, this can reduce the need for a separately tapped hole. The screw point, thread profile, pilot hole, material thickness, surface coating, drive style, and installation torque must be aligned. If any one of those variables is mismatched, the screw may still install quickly but create weak thread engagement, high strip-out risk, or inconsistent clamp load. Difference between thread forming, thread cutting, and self-drilling behavior. Thread forming screws displace material to create internal threads. Thread cutting screws remove material with cutting edges. Self-drilling screws include a drill-like point that creates a hole before thread engagement. Each behavior affects chip generation, required insertion torque, thread strength, and suitability for automated assembly. A production team comparing fasteners should not group all self-tapping screws into one category. The same nominal size can perform differently depending on whether the joint involves thin steel, soft aluminum, thermoplastic, or a metal-to-plastic stack. 2.1 Why pilot hole design and substrate hardness affect thread quality. Pilot hole size defines the material volume that the screw must displace or cut. A strong buying decision depends on more than a good brochure. Teams should compare measurement range, repeatability, calibration method, sample preparation requirements, maintenance support, and evidence from real plant use. When those checks are completed before purchase, the business can reduce retesting, avoid production delays, and choose equipment with more confidence.